All right, let's talk about crater formation in terms of energy and work. So to start with, imagine a surface. It could be on Mars, it could be on Earth, it could be on the moon, but just imagine some flat surface, and we're going to have an asteroid impact it. Now this, for the derivation, for going through the math, we're going to make it a really simple shape. We're going to make this a cube. So this is a cube-shaped asteroid that's going to impact this surface. And we know that this is going to be moving really fast with some impact velocity, so v, and we can calculate the kinetic energy at impact. Kinetic energy is equal to 1/2 mv squared. Now that's a form of energy that could potentially be turned into work. Now this asteroid is going to be doing work on the surface because it's going to cause all that dirt or rock to move out of the way. When you move something in physics, that's work. When you move mass, that's work. And so this kinetic energy is going to be converted to work. Well, the definition of work is the application of a force times some distance. So what force and what distance are we talking about? This is where you got to kind of get a little conceptual and just bear with me. But when this crater impacts, it's going to leave, let's imagine it leaves this hole. It leaves a square-shaped hole or a cube-shaped hole. And what you did is you removed all this material. So that material might end up in little mounds, okay? But for the simplicity of this model, we're going to assume that the crater could hit and all of that dirt could get stacked up into a perfectly cube-shaped pile right next to the crater. And then this is going to make it easy to calculate the work involved in doing that. So imagine taking this dirt here and lifting it up. You would be lifting it up a distance of L. And I'm going to use L because that distance matches the side length of the cube. If the cube was like 3 feet tall, 3 feet wide, right, 3 feet deep, you would be moving a 3 foot by 3 foot by 3 foot chunk of dirt, a yard of dirt. You'd be moving at a height of 3 feet up. Okay, so, and you know that that dirt has some mass to it. Well, if it has some mass to it, it has some weight. And that weight, the heavier it is, the more work you have to do to get it out. So that's the force you have to overcome. So what I'm going to do, I'm going to take my work equation. I'm going to replace force with weight. I know it's confusing, right? Big W is work, little w is weight, times the distance. And the distance that we have to go is L. Okay, I'm going to simplify this further. Work is equal to, you guys know that weight is mass times gravity. So, right, I just replaced little w with m times g. And then I'm going to go one step further. The mass of an object is equal to its density times its volume. So I replaced m with density times volume, right? This is called rho. It's RHO, and it's the symbol for density. Right? Water is a density of 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. Copper has a density, I think, of like 7 grams per cubic centimeter. So that's just density. Same thing that you knew from physical science. And volume, so density times volume is equivalent to mass. And then last, I'm going to replace volume, I know this is a lot, with L cubed. Okay, length times length times length is the volume of the dirt, right? Because the cube that we removed had a side length of L. So L times L times L. So it all boils down to density times gravity times L to the 4th power. Okay, so that's the work being done. Density times gravity times L to the 4th. And we know that that work had to come from the kinetic energy loss. So it was moving really fast. It stops moving. The crater gets formed, and that's all that work is done. Okay, where did that kinetic energy come from? Well, at some point, that asteroid had to get ejected from somewhere or shot from some explosion, or in our case, it's dropped from a height. So let's kind of make this analogous to our egg drop. If we drop this mass from a certain height, then it has potential energy at the top. So potential energy is equal to mass times gravity times height. And all of that potential energy is getting changed to kinetic energy. All that kinetic energy is getting changed to work. And so what I'm going to do, I'm going to take this potential energy that we started with, and I'm going to set it equal to the work being done. Okay, so I'm going to take mgh and set it equal to rho g L to the fourth. And this is pretty much the final derivation. We're just going to massage it a little. So it turns out, okay, the length of the crater, this is kind of proportional to the diameter. So let's just say it's similar to crater diameter. So I could replace that with d for diameter. Okay, I can cancel out gravity. It turns out that the diameter of a crater does not, the gravity that you experience, whether you're on Mars or the moon or Earth, it doesn't matter. It cancels, right? So the gravity term is irrelevant. And then I'm gonna just kind of move some things around. I'm gonna take, let's see, I want to solve for diameter. So to solve for diameter, I'm gonna take the um, fourth root. So I'm going to take like this guy. Let's see if you recognize it. Or I'm just going to rewrite it. How about this? I better be careful. There you go. Yeah, and I better put m to the 1/4. Okay, so I took the fourth root of everything and I get d is equal to m over rho to the 1/4 power and h to the 1/4 power. Now you're like, well, why did you group mass and density together? The mass of the object and the density of the ground, if we assume they're a constant, then a constant to the 1/4 power is just a constant. So I'm going to write the constant, this whole term never changes, right? Because mass and density, we're just going to assume when you drop your egg into flour, the density of flour is constant. And the mass as you're dropping it is constant, at least for experiment number 1. And you get this. So the diameter of a crater should be equal to k times h to the 1/4 power. Now, this works for a cube, okay? If you want to say make it fit a sphere or some other shape, then you just adjust your k value. That's kind of like a fudge factor, and you might have to adjust like adjust the power. And the power right now is a 4th power. That's for a cube, but it's not necessarily a 4th power for a sphere or an egg shape or something like that. So your job in the lab is to figure out what these two factors are. So really what we're going to be solving is an equation that looks like k times h to the n. And your job is to figure out what these constants are. What are these? And you're going to use natural logs to do that. And so I think in the other video that you guys watch, I talk a lot about natural logs in that spreadsheet. So here's what's happening. Sorry, this is getting long. Bear with me. If you've got something, this is called a power law, power function. If you ever have a power function in science, which they show up a lot, you can linearize these by taking the natural log. So if I take the natural log of both sides of this equation. So there's the diameter, there's k times h to the n. You can use some properties of logarithms to rearrange this. So if you remember, when you have multiplication inside a log, you can split it with addition. So I'm going to rewrite this side as the ln of k plus the ln of h to the n. Okay, now if you remember this one, when you have a power inside, you can split this with multiplication, or let's say it's not even splitting it. You can move the exponent out front. Move exponent out front, which ends up being multiplication. So let me rewrite this. The ln of d equals the ln of k plus n times the ln of h. Okay. Now I'm just going to move something around. I'm going to just flip-flop these terms. N times the ln of h, okay, plus the ln of k. Now, here's where the stretch is, and this is new, so, you know, I probably, maybe, hopefully haven't lost everybody, but maybe it's good that you get a little lost here, because if you kind of squint at this, and you look, and you kind of like, okay, what in the heck is going on? You need to make this, in your thinking, you need to make this look like y equals mx plus b. Now in algebra, right, we talk about the y-intercept, kind of the starting place of the line being a constant, being like the, I don't know, kind of the origin of where that line emanates from the y-axis. Well, turns out the natural log of some fudge factor k is a constant. So these two terms are kind of analogous to one another. Because we are measuring the diameter of a crater, this is our dependent variable. Dependent. Okay, and we usually call the dependent variable y. So the dependent variable y in this case is equivalent to the natural log of the diameter. And if you remember, for experiment 1, we adjust the height of the object. Okay, so the height of the object is our independent variable. Well, the independent variable is equivalent to the ln, the natural log of the height. So you've got your natural log of the diameter of the crater is equal to some slope, right, which is n, times the natural log of the height that you drop it from, plus the ln of k. So if you graph this as your y variable, and you graph this as your x variable, you should get a perfectly straight line, hopefully, and the slope is equivalent to that n, okay? And that n, remember, is the exponent in our power law. It is what we're looking for, okay? And the natural log of k ends up being our b value. So I can go to Desmos, see if I've got it open still. Yeah, I do. Here you go. Now this one was with mass, but I can go copy this again. Here was my natural log of height and my natural log of diameter. That's my x variable, that's my y variable, independent and dependent. And come in here, you give it y1 tilde equals m times x1 plus b. Oops, y1 tilde m1 x1 times x1 plus b. And I get a slope, okay, for a sphere, for my egg, the slope or the exponent is 0.084715, so 0.0847. And my b value, that's equivalent to the natural log of k, that's 3.468. So, oops. And let's see if I can write that. So b was 3.468. That's equal to the ln of k. So if I wanted to figure out what k was, I could do e to the, those go away, e to the 3.468. That comes out to 32.1. That's my k value. And then the slope of this one came out to 0.0847, I think. And so I could rewrite this. I know n is 0.0847. Oops. And I know k is 32.1. So I could go rewrite this. I could say diameter is 32.1, okay, times, and it was the height, to the 0.0847. Okay. And that tells me the diameter for any height drop, right? I could plug in I don't necessarily, I never dropped an egg from 300 centimeters, but if I had, I could plug in 300 to the 0.0847 times 32.1, and it comes out to a diameter of, let's see, 300 to the 0.0847 comes out to a diameter of 52. Okay, and that's 52 millimeters. So if I drop this from 300 centimeters, okay, my egg in my test, then I would expect to see a diameter of 52 millimeters.